This is a procedure of how I run multiple reads on my QIC cartridges using my universal QIC reader. And each time I read a track, if there's a problem on it, I'll reread the track, but not at the same location. I will use the track adjustment tool that I demonstrated in a previous YouTube video to move it down by, let's say, half a turn or a full turn. And I'm counting turns of the knob. I'm not counting turns of the motor that is it the motor? Yes. Not counting the turns of the motor that moves the head up and down. So I think a full turn for the knob is a half turn for the motor. Therefore, I'm dealing with half turn and quarter turn adjustment increments on the actual physical adjustment of the head. And please refer to my Universal QIC tape reader videos if you have more questions about how that works, particularly the one about the manual track adjustment feature that I added. Now, I'm finding that on marginal tracks where there's a number of block errors, hopefully less than, let's say 100, because if there's more than 100 block errors, then this becomes a very arduous process. But there's always a way to whittle down these errors. So this is an example of me finding individual block errors that are identified by my programs here, and on a different read, a number of different turns down of the knob or up of the knob, that particular block was read just fine, but others error out. So we just piece these things together. Now, unfortunately, right now, this just seems like a manual process. I'm sure I could automate it if I was going to do hundreds or thousands of these. But for right now, this is the general process of what I do to replace these, just to have a look at what it looks like. So the master file that I like to use is the data block bytes report. And this is a report that my programs create from the data pulses that I capture on the Saley logic analyzer. There's thousands of lines of code that I wrote and multiple programs that run in succession in order to get here, and they're very specific towards the format of the data pulses that are written on the tape. You know, the format of the magnetic flux transitions. I'm using the term magnetic flux transitions and data pulses interchangeably here. So this is the report that I like because it gives me all the information I possibly need on on each block of data. And what I'm dealing with right now, it just happens to be a QIC 11 format data. So this is a QIC 11 formatted data block. And so please refer to my web pages about how how those formats work, how they look, how I reverse engineered them, and how what the anatomy of the data block of a QIC 11 data block looks like, the anatomy of that data block. Okay, so it's really just a simple swap. I've identified that this one is a problem. We have a CRC calculation mismatch here, actually. The written CRC is hexadecimal 3112, and the calculated CRC came up as 44D2. There's the decimal equivalent of those, just in case you were interested. I don't think that matters here. What matters is they don't match. But reading the track with a slightly different alignment yielded errors on other blocks, but not this one. So we simply copy and paste. Still a little bit manual, as I said, but here's how that looks. Here, this very same data block was read successfully. The CRC of 3112 was actually calculated of 3112, which means that there was probably one byte or even one nibble that was off. And I think it was one nibble, half a byte that was off, misread, but it didn't cause other errors that cascaded throughout the rest of the block. So we'll just do a replacement here. Now, it just so happens that the using Notepad on Windows here. And I have word wrap off. And even though word wrap is off in Notepad on Windows 7 is what I'm using today, the line still wraps at, I believe, 1,024 characters. And so this is actually a 512 byte string, but it's made up of the hexadecimal characters. So let me show you what I mean by that. So here's the 1024 hexadecimal digits or characters that actually make up the 512 byte data block. So if I were to paste those here into my hex editor, I just happen to be using HXD today, then we see that we actually have 512 bytes. 480 plus 1 would be 512 right there. I should say 420 or 480 plus, what's my offset, 32? So what we have here is a full 512 bytes, or 1024 nibbles. I guess we're working with nibbles here because a nibble is half a byte, or 4 bits, and those 4 bits are represented by a hexadecimal character. Okay, so the reason I'm saying all this is because this line just happens to end right at the end of the block. So all I'm doing is copying this, and I'm making sure that I don't copy the data block number, which is 7C, the written CRC, which is 3112, or anything after that. And these are the characters that I'm using to denote a postamble, a preamble or postamble that comes after that. So 7C3112 plus the rest of this is something that's not part of the data block. And just in case you want to see how that works, 7C is the block number. I have my programs have spelled that out right here and given me the numeric equivalent of that. And they have also spelled out or I should say, reprinted, redisplayed. That's what I really wanted to say. Redisplayed the CRC here that's written on the tape, and it's also given me the decimal value of that. And just so you understand what these things are. Now, my program does something that is incredibly helpful. It keeps track of every block that it finds sequentially on the entire track, from 1 to however many blocks it finds on the tracks, including erroneous ones and ones that might be a block but really aren't. And my program was just, given a head fake by the signals on the source logic analyzer dump. So this is incredibly helpful because it allows me to find the same block in multiple reads, assuming that one read didn't pick up a hint of a block or a false block that the other one didn't. And even if it did, we can still figure this out because you can look at the context. And here with QIC 11 or 24, but this is 11, it's even easier because you just look at the block number sequence that's written, and if it matches, you should be in good shape. So let's go over to the bad block here. This is the bad block. And we see that the bad block, I don't know if this number is right because the block is bad. So I cannot assume that the block number it found here is right. The block number in the following block is definitely bad. We'll get there in a minute. The block before that is fine. The CRC checks out, and all the blocks before that are just fine. And so that we see that this is block sequence 122, 123, 124. We see that this is block number 124 in the sequence. The QIC block numbers go from 0 to 255, and oddly enough, they start out at 1 on the first block of the serpentine stream instead of 0. I don't know why, but it goes from 255 down to 0. So that's why you see a sequential block count on this is a multiple higher than the block number that's being reported by by what's written on the tape. Okay, now that we understand that, this is still valuable because we see the sequence here: 123, 124, 125, 126. So I'm definitely missing blocks number 124 and 125, or sequentially blocks number 897 and 898. So I go over to a different read, and I go to the data byte blocks report that I have from the different read, and I see what block am I dealing with. I like to search for my sequential block number because those are truly unique throughout the entire file. So block number 897 should be entirely unique. There should only be one of those, particularly with this timestamp address that I put in there in case I need to dig down all throughout my programs and all the way back to the original logic analyzer dump and logic analyzer graphic representation. But let's just swap these out. Hopefully I've explained this well enough. So we see here that this is a good block, so we can just swap the good block out for the bad. Now, my programs, I have additional programs that read this file and dump that to a file that I just paste into the hex editor, and it shows me, close this here, it shows me where I have bad blocks with this notation right here. It's not a full 512 note, but I didn't want to waste all that space, and this was easier for me. So this was one of the indicators that I had that there was a bad block here in sequence number 897, and in order for me to replace it with the valid data, all I have to do is make sure that I have selected the area over here to the left, which is a hexadecimal, and not the area over here to the right. Notice which one is darker blue. The hex editor says this is the ones you selected and this is what you represented, versus this is the ones I've selected and this is what it represents. So this is what I want to select, and I will simply copy the good block now that I'm confident it is the correct one that belongs in position number 897, and paste it in. And there it is. So this is that block. And yes, it does happen to be a bunch of repetitive characters. I think this is a hard drive backup that has put unique characters on every block, something like that. I'm not sure. I'm not going to go too deep into the speculation about why the data is what it is. But the point is that I'm using all of the design tools that are available to me, and including the cyclic redundancy check to verify that that block actually is correct. So I believe that it is. So I can save that, and I can do the same thing now with block 898, because that one is bad as well. And it just so happens that block number 898 is good over here on this read as well. Let's, just for curiosity, let's see what was wrong with it over here. My diagnostic actually tells me what was wrong with it. This one was a CRC calculation mismatch. And I compared them. I found the nibble that was bad, but I won't put you through that pain. This one has a lot of warnings. Look at all this. It finds unrecognizable characters at 344 nibbles into the nibble count. It contains, another. It's a bunch of things that shouldn't be there. So I think there was some kind of missing data pulse, missing magnetic flux transition or something, or maybe an extra one, and it shifted the whole thing byte-wise, or bit-wise, I should say, and just messed up the entire block. So that's what was wrong with this, and as a result, we couldn't calculate what the block number was. My program couldn't calculate what the block number was, so it's designed to just put X's here. So, it's a bad block, and for this video, we won't go any further into why it's bad and what all these things mean. We can go into that later. But the point is, I've gone to great lengths to figure out exactly what's wrong with it in all these cases. But good news is, over here on this read, it's correct. Block 898 is just fine. So we're just going to do the same thing, copy that over, and make sure that we select this section right here and paste that in. Excellent. Now I'm going to undo this twice. And I can't undo that. Why can't I undo that? Because I saved it. I'm going to check my video. I seem to recall that the note previous to that was longer than this note. I don't know if there were different programs that wrote that. I think it was different programs that wrote that. Yes. Get to that later. But I just wanted to demonstrate how the manual process that I go through to now replace bad blocks one by one so that I can get a file that is verified all the way through, even though I can't actually read the whole track from beginning to end. And there we have it. So hopefully this was beneficial to you, and I thank you for watching.